Hi, I'm John Marshall. As he said, I have a Marshall Laboratories here in Boulder. We're kind of an R&D group that's survived by doing anything we can to get contracts. I'd like to make a correction to the title of this talk. The magic important word is missing from the beginning of the talk, which is plasma catalytic separation of CO2 on Mars. It makes all the difference as far as the chemistry involved. The things I'm going to try to tell you in this talk are first, how to get rocket fuel much quicker than any of the plans before. I have to explain that I'm a total newbie to the Mars Convention. I certainly plan to come in the future. So it's been an enlightening morning to all of the wonderful ideas that are going on. Anyway, in order, I think I can show you how to get rocket fuel much faster because of plasma chemistry. Second thing is I've got to read my own handwriting. Oh, the second thing is to leave behind a capability for doing fuel production, for making important chemistry. After, say, people return, there's a good way to do this, I think, in what I see you. I have to admit that we've only had, well, a week. The two gentlemen in the front row here, Mark McDonald and Mitch Randall, will tell you we've had about 2 days to put this talk together. Okay, but I think you'll still like what I have to say. The third thing is how to build an energy industry on Mars that's going to support sustainability and support future civilization on Mars, support the cities, the networks, the communications, the transport, all of those things that Jim Brown was talking on his list. What I want to see here is a little more like Kennedy. This needs to be done in less than a decade because I'm getting too damn old and I want to go on the ride. So there's just one point of order I want to make. I mean, all of the things we're talking about that are the knowledge we have. Geo and Terra don't apply. Maybe you think I'm nitpicking, but I think the words are important when you're talking to humanity. And geo means Earth, and Terra means Earth, and so terraforming is meaningless, and geophysical is meaningless, and geochemistry is meaningless, and geophysics is meaningless. We need a new word. So Ares is the Greek god of war. Mars is the Latin god of war. I want to know from you people what we're going to call this, because the word is important. Let's have aerochemistry, or marochemistry, or marophysics, or whatever, okay? Because then we can talk about what we're really onto here. The problem with Ares is I don't want to talk about anything being Aryan because it sounds wrong. So I would love to hear any suggestions. The words are important. We should make something that's specific to Mars, because what I'm going to talk about here is how you don't design in relation to what we have here on Earth. There's too much of saying, well, the pressure is different on Mars. The temperature is different on Mars. How are we going to do this? How we do this on Earth? By pumping, by heating, by whatnot? No, you need to live. You need to put your mind right on Mars, and you need to go with the flow. You need to go with the chemistry of Mars. You need to go with the temperature of Mars. You need to go with the atmosphere of Mars. I mean, all the chemists we have here, first thing they're trained to is STP, stands for standard temperature and pressure. Standard? This is what? MTP. You got to think MTP, Martian temperature and pressure. Everything important I'm going to talk about is based on glow discharge. Okay, so bear with me. You think, what the hell is glow discharge? Everybody here has experienced glow discharge in their everyday life. See these lights up here? Those are fluorescent lights. That's a glow discharge going on in there. Everything I've been doing for the last 20 years is also going on there, which is a process called sputtering. And sputtering goes on in those lights. If you look at the fluorescents that have burned out, they got a little black stripe around the end inside the thing. That's because the tungsten filament sputtered onto the inside. I mean, argon atoms hit the filament, knocked atoms of tungsten off and put them on the inside of the light bulb, which is the same reason they burn out when you see the black stripe. The filament got eaten away. So anyway, those three things: rocket fuel faster, an energy industry for stasis and stability, homesteading, everything that Jim Brown was talking about, the hydroponic greenhouses that you're going to need to sustain life on Mars, so you have waste from the greenhouses to feed Heather's worms. And the worms, in turn, you see, give back the nitrates and phosphorus that you need to feed the plants. It's a nice symbiotic loop. What? Oh, yeah, sure, the plants generate the oxygen for any biodome as soon as you get them going. Anyway, let's get to glow discharge. How much time do I have? Any idea? Thank you. Glow discharge that's going on in these lights overhead has a cathode end, just like the electropropulsion drive. It has an anode end. It operates at typical voltages. I mean, those things up there are running at about 150 volts because that's the AC peak. I mean, they say 110 volts. That's RMS voltage. It's the peak voltage that fires those light bulbs up there, but they're all glow discharge. And if you look at the thing at the cathode end of this thing, you say, I mean, this is the cathode end over here. There are almost no electrons coming off of a cathode. Well, that's because the ions pick up the electrons from the cathode. This will be important because what I'm going to talk to you is an ion generator that makes possible the energy industry on Mars. This is a device I built to clean hard disks. Okay, it is an ion generator. Over here are the substrate disks I was trying to clean. I'm not going to explain how this works. It's proprietary. I'm not going to explain what's on the disk because that was the catalysis and that's proprietary. However, there are a zillion catalysts, so the hint here is any catalyst is going to work with this new plasma chemistry. Here, of course, is where we need to mine our fuel. For making rocket fuel, we don't have to dig an oil well, you just use this. An interesting thing about plasmas, has to do with the fact that there's a right-handed rule in physics that I like to do, left-handed, okay, because I care where the electrons go, and this cares where the ions go. But Mitch here has been nice enough, he's the physicist, to run the numbers and try to get us what happens here if you do what was getting talked about on Mr. Brophy's, Dr. Brophy's ion drive, is E cross B fields. In this case, B is the magnetic field is vertically through this thing. The E field's across it, which means that you have the force around the center thing here, and this thing rotates its stuff. You get plasma rotations that are in relation to the speed of light. Here's the formula up here. That little c there, it's nice to have a c in an equation because that's the speed of light. Okay, so do you think we can rotate some plasmas? I think we can rotate some plasmas, and they're going to go real quick. And here's just a thing, and there's where this came from. It's one of the most beautiful standards in plasma physics that's been around since '83. One hell of a book. Anyway, we're going to do some plasma rotation to build the energy on Mars, energy industry. Here's an early thing that used arcs. Okay, so they had these kind of Tesla coil arcs zipping around in here. I mean, because you can do catalytic chemistry with this type of thing, but the arc only exists somewhere in there. It's not plasma all over the place. It's just kind of a Tesla sort of thing. You know those little globes you put your hands on and they're little sparks inside of the thing? It was kind of like that. Actually, those could do catalytic chemistry if somebody wanted to adapt those to the house. Here's a paper that I've got right here. It's somebody arguing for doing, it's a bunch of Frenchmen and Germans and I don't know, Spaniards, I mean European scientists, arguing for doing what's called low temperature plasma catalysis. And I mean, I love this line in the paper here because it says, due to its low pressure characteristics, the glow discharge is not very suitable for chemical synthesis. Yeah, not very suitable for chemical synthesis. Here on Earth, you know what? Mars is the most perfect place. Don't mariform the place, the atmosphere. I'm having CO2, and I mean, it's perfect. 6 millimeters, I can run a glow discharge in 6 millimeters of atmosphere on Mars. This is real chemistry. This is the energy industry on Mars. Here is our processor. Okay, the front end, you take in Martian atmosphere. All those little veins inside this thing are coated with catalyst. I mean, we've heard a little earlier from Robert Zubrin about how all we have to do is split off the carbon monoxide and do the Sabatier process. Well, I mean, Raney nickel, things like that have been known since 1900. We use that catalytic process to light all the cities on the East Coast with methane. We generated it from coal. We used it with, you shut the door on a coal fire, you throw in water, you have nickel, and bam, you get methane out of the thing and you can send it to the street lights. Well, this baby's a little quicker. It does look like a jet engine, doesn't it? Looks like a turbine. Yeah, something like that. Well, it's all coated with catalyst on the inside. This little element right in the middle of this thing, up there, is the same plasma ion generator that I showed you at the beginning that I was using to clean hard disks. Okay, so we can run at 6 millimeters pressure on Mars, CO2 plasma inside this thing that totally coats the inside of this thing with plasma. And I mean glow discharge plasma, which means we're in a major high temperature regime. Not only that, because this thing's also wound and magnetic field is along the length of this thing, electric fields across, and so we're going to have velocities, throughput velocities in relation to this thing that the parameters of the equation are going to say are part of the speed of light. So this processor, this catalytic conversion of CO2 operates, I mean, you run any diameter size of this thing and you're starting to talk millions of cubic feet per hour, okay? And this is how we're going to get rocket fuel in 1 month instead of 8 months. This is a ringtail sputtering magnetron that I developed. This is not for, it's not the ion source. It looks very similar. It's all on the same principles of my left-handed physics. Where do the electrons go? I like being left-handed because then I'm in my right mind. This deposits materials. Using this device instead of the thing in the last photo here, the central ion generator, all I do to build my catalyst is I put this in. I can put down any metals on these cylindrical cathodes, any important catalytic materials, and sputter them down, deposit them right on the inside of this device. So any catalytic process that's ever been used in the energy industry, namely oil refineries, can be done with this one instrument at ambient pressure, ambient Mars pressure, and any of the processes. I mean, here's a nice close-up Mitch is responsible for this beautiful thing. Here's the front end of our processor. This thing, maybe on the first Mars flight, we make it 6 inches in diameter in a 20-foot long tube. But at any rate we run it at, CO2 goes in the front end, and O2 and CO come out of the back end of it, and at a very high rate. Here it is on Mars. I mean, we took the photo. We had to take out the legs on it. I hope you know that they were there. So what's this stuff? Well, it's distillation first. You get all this black crud out of the ground, and then you distill it off, and still you got all these partial things. But then it goes to what's called mixed bed reactors, catalytic fluidized bed reactors, cat crackers. I mean, there are all of these different things that these people do. These people make money. They make a lot of money. They don't seem to pay a lot of taxes. Oh, well, get off of that bag. But, I mean, look at this. We don't have to dig up one thing. These guys got to go and drill 15,000 feet into the ground or into the Gulf of Mexico, and maybe have to try to stop leaks and various things. Okay, all of the carbon source. I mean, the nice thing about Mars, it's got one hell of a carbon footprint. So I mean, look to the right here. That little flare gas, that's the stuff they're throwing away because there's not enough caloric content in it to do a damn thing. So you just burn it off. Okay, because here we got oxygen, so you can throw it away. There's no point in throwing it away with this. I mean, this that I just showed you. You just feed it back in after you get to the point that you get CO and O2. I'll show you how you separate with the same device the CO from the O2, because what do you want to feed to the what you want to feed to the catalytic process that will get the rocket fuel to come back from Mars is just the CO. So you want the oxygen out of there. Happens to be useful because people do like to breathe, but mostly on the first mission, unless we store it somewhere, we have to throw it away. On the other hand, maybe the worms might like it, or the plants, the hydroponic plants that ought to be left behind in automated greenhouse growing, which is quite done. The people with the highest budget for growing automated growth booths more than 30 years ago was the people who were growing the highest cash crop in California. There's been a lot of talk about it in medical industry or recreational use in Colorado. I don't think I need to talk farther about what it is. Those people were doing automated blockhouses that they would drop in 30 years ago, and they could walk away from, and then they just came back when they had to harvest. That's some of the stuff of what this stuff is. We don't need any of it. Throw it out. What I just showed you, putting down the catalyst, is all of this and more. We're into the plasma chemistry makes it all possible with the one rotary whiz bang I showed you there. Here's something interesting about plasma. I mean, this was in that same paper where people are arguing for, oh, we got to go to cold plasmas because the old plasmatron things were energy hogs. Well, I worked in that lab with Willard F. Libby in 1970, 1969, 1967 at UCLA. We were doing nothing but catalysis. Okay, and a guy named Lowell Wood had what was called a plasmatron. You'll see it on this thing a little later. I better hurry along. I don't have that many minutes. Anyway, on the left-hand side, the white part is the specific yield of product you get using plasma only. The black parts are when you have the specificity of the catalyst getting you what you need, okay? The white parts are so short because if you just put hydrocarbons into a plasma, you get everything. I mean, it's the Murphy's Law of chemistry, which is with a plasma, if it can happen, it surely will happen. Here is that wonderful paper on the right. Over here is one of these points could just as well be Lowell Wood's plasma torch. This plasma catalytic conversion thing. You have oxyacetylene, and then you put in an enormous amount of electrical power to try to put the temperature through the ceiling. Okay, but both of these things in this paper are still what I call thermal plasmas. They aren't above 10,000 degrees. Okay, well, 1 electron volt, the equivalent of 1 electron volt is 11,000 Kelvin. And the things that Jim Brophy was showing you, any of the plasma things, any of those things up there, that thing up there is operating at 150 electron volts. 150 times 11,000 Kelvin. Okay, so if you want temperature to do chemical reactions, 150 times 11,000 is a big number. Anything that can happen will happen. You got chemistry. Oh, let me do one more point here. Our device is about here as far as the energy input. However, the throughput, I mean, they normalized over on this axis for getting the specific chemical they wanted, okay? What you really want for throughput for an energy industry is metric tons per hour, okay? And that's what this baby can do that I'm showing you. Okay, anyway, we're off the friggin' charts. Here's our important reactions. I mean, we only have to go as far as the Sabatier reaction to get the specific impulse that we need. I mean, methane's a spectacular fuel. Thank you, Robert Zubrin, for educating me a little more this morning. So, I mean, there's only one step originally that we have to do with our turbo mixing catalytic plasma super thing. And that's to get methane out of it. But there's far, far more, which is stasis, stability, and society on Mars, industry, metallurgy, namely right here. All that red stuff is iron oxide. You want to release some oxygen, then you have enough energy to stick an arc thing in and run an arc furnace, start making yourself some steel, build some buildings. You know, and a nice byproduct of it is all that oxygen. I mean, just like the flat irons over here, half of that red stuff is oxygen, Fe2O3. And so why not release it into the atmosphere? Seems like a nice idea to me. Here's a neat power module that a bunch of runaway Los Alamos scientists do. I don't know. I mean, I heard this morning maybe we can't bounce this thing onto Mars yet. But this is a whole lot more than 100 kilowatts. It's a nice small reactor. It's absolutely bomb-proof, bulletproof, self-regulating, good for 5 years, and I believe it's something like 750 kilowatts. Okay, well, this makes an energy industry if this is the power source for this thing. By the way, I mean, you do it in a 6-inch diameter, what I showed you for getting the carbon monoxide and oxygen. We can do that. Give me 25 kilowatts and we can run it no sweat. Whoops. For the test thing, I was just in Boston, exactly where this item was made. It's called a space test chamber. I believe it was made for Martin Marietta. The test I want to run on our little plasma catalytic turbo reactor there ought to be done inside of a chamber like this. This specific chamber can be run all the way from about 20 Kelvin to 150 C. You can have any atmosphere or any vacuum inside of it you want. The company that builds this is in Dynavac, and as I say, I was there for a week just a little bit ago. Oh, how'd that get there? Oh, yeah, this is important. Since I want to make rocket fuel very quickly, and since the guy on the left realizes that it's a problem to get the rocket fuel to get back, I just kind of like him to know that I want to solve the problem for him. That's why I'm standing out there with the can, because he's already advertised that the tickets are $500,000. But, you know, gee, if I pay for the fuel or I help with the fuel, I mean, can I get a free ride? Which is another reason why I want to see this happen in less than a decade, Because if it doesn't happen in less than a decade, I'm going to be 80 years old and they won't let me go. So hurry up, guys. Look, it's the people in this room, it's the people at NASA, it's the people at the other space agencies. That's all of us that there are. I'll say one more thing, which is that there have been a lot of big advances for mankind. I mean, I'll just start with the Manhattan Project. I grew up with all of those people. That was the biggest advance in technology that ever happened. I mean, because that was the nuclear age. The next biggest advance that gave us technology, and the reason why we've got composite materials, the Dreamliner, the reason why you're holding cell phones is because of NASA. The reason why you got non-stick frying pans and why we got the society we got today. And so we need to put some money into something reasonable. I mean, it's just suffering inexcusable, the budget that goes to NASA, the fact that we don't educate our children in this country and pay for their education. Don't get me on that soapbox. Anyway, look, get on the positive side. I want to hitch a ride. I want it to happen soon, so I'm not too damn old. I would like to thank Dr. I mean, all of these people are dead, you know, but I'll thank them posthumously. I want to thank Willard Libby, Nobel Prize for carbon dating, who was my mentor and professor on catalytic types of stuff at UCLA in 1970. His wife, Leona Marshall Libby. Dr. George Gamow, who was interesting in teaching me about the universe and things like what 99.999999% of the universe is made of, namely plasma. And also my father, Dr. John Marshall Jr., who was an excellent experimental plasma physicist at Los Alamos. Created the plasma gun that is still today the injector for the tokamak types of fusion devices. But most of all, is Robert in here somewhere? Well, let's applaud him anyway, because I want a special debt of gratitude to Dr. Robert Zubrin. He will deserve the credit in the near future for a great leap for humanity and a quantum leap for mankind. Thanks very much.